Hello, this is the first in our series of 3 response questions from the released 2012 AP Calculus exam. And this is FRQ number 1. That means it's calculator active, so make sure you have your calculator handy so you can follow along. This FRQ is a word problem all about the temperature of some water, and we are asked to calculate various things to do with this temperature function using things like our Fundamental Theorem of Calculus, a Riemann sum, all that good stuff. Let's dive in. So in part A and throughout this problem, we're working with this table of values. We are given this temperature of this water at these various moments in time, these t values at these various minutes in this table. The first thing that we're asked to do is estimate W prime, the derivative of that temperature function, when t equals 12. We're asked to show our work and also interpret our answer using units. So before we do any of that, I want to just zoom in here on this little graph that I've plotted using the table of values. Now, you don't have to do this. You probably shouldn't do this under timed exam conditions. But here, I think it's going to help us conceptually understand what's going on a little bit better. So these are my 5 points that I'm given in my table of values. And that's all I know about this function w. Now, the full graph is probably doing something smooth and continuous like this. It's sort of vaguely increasing. And we're asked to calculate W prime at t equals 12. So t equals 12 is right here. So up here, I remember that my derivative is the slope of my tangent line. So let's say my tangent line looks something like this. Well, it's a bit chunky. Let's make it a little bit slimmer. So my tangent line is looking something like this at this particular point on my graph. And I want to estimate the slope of this tangent line, which is W prime of 12. Well, if we think back to how we first set up the idea of the slope of a tangent line, we can always approximate it using a secant line, the slope of a secant line. So if I look at 2 points nearby, and I genuinely do know those 2 points, they came from my table of values, I can use those to set up a secant line, use my rise over run formula to figure out the slope of the secant line and say, aha, that's probably going to be pretty close to what the slope of the tangent line is. So with that in mind, we're in pretty good shape because we can approximate this as rise over run using my 2 points there. So I've got t equals 12, so I'm looking on either side of t equals 12. So I have these 2 ordered pairs. So I'm going to do w of 15 subtract w of 9 all over 15 minus 9. That is 67.9 subtract 61.8 all over 6. And if I go onto my calculator, that's 67.9 minus 61.8 all divided by 6, which gives me this long, probably infinitely extending decimal, but if I'm rounding to 3 decimal places, that'll be 1.017. So that is 1.017. So that is my approximation. I've estimated that value. I've certainly also shown my work. And now we need to interpret what this answer actually tells us about the temperature of the water, the context of the problem. So it's all about remembering what W prime of 12 is. This tells us that the water temperature at T equals 12 minutes, we definitely want to remember our units, is increasing at a rate of approximately 1.017. That was my approximation right there. Remembering my units though, I'm measuring temperature in degrees Fahrenheit. And what's my unit of time? It is per minute. So this quantity, the slope, this W prime, it is a rate of change. My water temperature is going up because it's a positive quantity. It is an increasing rate of 1.017 degrees Fahrenheit per minute. How were the points divvied up here? Well, we've got 2 points altogether. We're going to get 1 point simply for our estimate, and we're going to get 1 point for our interpretation, as long as we remember our units. If we don't remember our units, you're out of luck. In part B, we're asked to work with another quantity. It's a definite integral, this time of W prime, and we're again asked to interpret the meaning in the context of the problem with units. So before we dive in, I want to remind us what the Fundamental Theorem of Calculus sort of conceptually tells us, which is that if I start with a function, w, and I differentiate, okay, I by definition get its derivative, w prime, but the Fundamental Theorem tells me if I integrate w prime, I should get back to where I started, at least somewhat, okay? W prime integrates should give me w. We have to finesse that a little bit here because we're working with a definite integral, but that same theoretical underpinning is telling us what is going on here. So, to make that more precise, the Fundamental Theorem of Calculus tells us this integral, all I have to do is figure out an antiderivative of w prime and take the difference evaluated at the limits. So, by what I was saying previously, w is an antiderivative for w prime. I'll evaluate it at w20. I'll subtract off w0, just matching up my limits as so. And now I can read off from the table that w of 20 is 71. Oops. W of 20 is 71. And w of 0 is 55. I guess we're calculator active, but hopefully we know this is 16 without relying on our calculator. Aside, that's a really good point, but just because you have your calculator for each of these problems doesn't mean you always need to use it. Have faith in your own abilities, whether that's conceptual or calculation-based, to not always rely on the machine beside you. So here we've evaluated this quantity. That is great. Now we just need to interpret its meaning in the context of the problem. Well, as long as we remember what the Fundamental Theorem of Calculus tells us, this says the net change is represented by this integral. It's the net change from between t equals 0 and t equals 20. So this tells us that the water temperature increased by 16 degrees Fahrenheit between t equals 0 and t equals 20 minutes. Right? That is what this difference here is telling us. It's the change in the temperature between those times. How were our points divvied up here? Well, it's similar to part A. We're going to get 1 point for our value, 16, and we're going to get 1 point for our correct interpretation, as long as we, again, remember our units. Part C is probably the most involved, perhaps trickiest part of this FRQ, so let's really make sure we pause and understand it. L. So we're asked to use a left Riemann sum, indicated by the table, to estimate 1 over 20 times this definite integral, okay? Then we're asked, is this an overestimate or an underestimate of the true value of this quantity? And we need to explain what is going on. So before we do anything, I'm again going to zoom in on my plotted graph here. You wouldn't do this on the exam, it would use too much of your time, but conceptually right now, probably helpful when we're setting up our Riemann sum. So remember, our Riemann sum is just a sum of area of rectangles. And we have some points given to us by the table that will help us set up our rectangles. So if I look at each of these points, I can drop down some legs to the x-axis or the t-axis and set up some rectangles. Oops. Okay, so in particular, we're asked to use a left Riemann sum. So that means that each of my rectangles should use the height of the left-hand point on the graph. Okay, if I'm looking for just a second at this rectangle, how high should I make it? Well, I could use that endpoint or that point to make the height of the graph, whatever I want. We're asked to use a left Riemann sum, so we should use that left-hand point. So in particular, if I do that for each of my rectangles using the left-hand point, these are the different rectangles that I'm going to get, my 4 rectangles. So the Riemann sum is just the sum of the areas of these 4 rectangles. So let's write down the bases and the heights of these rectangles so we can figure out their areas. So it's fairly straightforward to figure out their bases just by counting along the horizontal axis. So I'll have 4, length 5, length 6, and then length 5 again. I could also have looked at my table and just figured out the consecutive differences there. Okay. Now we need to figure out the heights of our rectangles. Well, again, these are coming from the table. So this first height is just W of 0. It was my first entry. So that's 55. My next height is going to be this, which is 57.1. My next rectangle height is going to be this height, which is 61.8. And my final height is going to be that, which is just here, 67.9. As you've practiced lots of these problems, you're going to be able to jump straight to what I write down now without having to set up your rectangles. But just in case this is your first time, I wanted to show you all the messy details of those rectangles. So our approximation is going to be 1 over 20 times that definite integral. And that is what we are approximating using our Riemann sum. So I have my first rectangle here. The base is 4. The height is 55. Let's add on my next rectangle. The base is 5. The height is 57.1. For my next rectangle, the base is 6. And the height is 61.8. And for my final rectangle, the base is 5. The height is 67.9. Now you can see if we look at our table here, we really just use these 4 values, one after the other, using for our Riemann sum formula. So that's how you can sort of jump straight from the table to what we have here. Now, if we actually type this into our calculator, okay, I could go here, set this up as 1 over 20 times, and then type in my big long sum there. But in the interest of time, I'll just take it for granted. This is going to be roughly equal to, and I have it over here to the side, roughly 60.79. Okay. That's the exact value of the Riemann sum, and so that's approximating the value of 1 over 20 times this definite integral. So we've got that done. Now we think a little bit conceptually, is this an overestimate or an underestimate? Well, we do need to remember our function was increasing. We were told the function w was strictly increasing. So if I again draw my estimate for what maybe the graph was doing, it was maybe something like this, right? Well, the true value of this integral is going to be the area under that curve. Okay? And my Riemann sums have approximated the area, the true area under this curve is something like that. But my little rectangles have kind of missed some of what's going on, right? These little skinny pieces lie under the curve, but they're not taken into account by my rectangles, by my Riemann sum. So the true area is going to be larger. So our approximation is an underestimate of the true value because we were told W is strictly increasing. And we used a left Riemann sum, which meant that all of our rectangles were slightly too short. So how are the points divvied up here? We get 1 point for our attempt at a Riemann sum. We get 1 point for our numerical answer. And we get 1 point for our answer about the over or underestimate and our justification. Okay, part D, the home stretch. Now in this part, we're given some more information about what this function is doing beyond the edge of the table, right? The table only goes up to the first 20 minutes. And in this problem, we're being told what happens as t continues for the next 5 minutes up to 25 minutes. And over that interval, we're given an actual formula, an actual function rule for W prime, the derivative of this water temperature function. Okay, W prime of t equals this product of square root t and cosine and all that good stuff. And we're asked to use that to figure out what the water temperature is when t gets to 25 minutes. Well, again, we're going to use the net change theorem, calculate an integral using our calculator, get that final answer. So we're going to break this up into two pieces. So we're going to take the temperature at T equals 20. So that is my initial temperature when this function rule kicks in. And I'm going to add on the net change in temperature from T equals 20 to T equals 25. If we can figure out those two pieces, we'll be done. Well, the good news is I know exactly what the temperature is doing at T equals 20 because that is my final entry in my table. So I get 71 as the initial temperature at the start of this 5-minute period at T equals 20. And I want to add on the net change in my temperature. Well, we already talked about net change in an earlier part of the problem, right? The net change of W from the fundamental theorem is the integral of W prime over the interval that I'm interested in. So the interval going from 20 up to 25. Now the great news is they give us a formula for W prime. It's this thing here. So all I have to do is use my calculator, remember how to calculate a numerical approximation of a definite integral, and then we'll have our answer. So let's dive into our calculator. So we need to remember we're going to hit math, and that's going to pull up our math menu. And then it's the 9th entry on there. It's fn int, function integral. So here, well, I have leftover work from earlier on. So let me just clear all of this because that's going to mess me up. So again, we'll do math, entry 9. So math then 9. And I know I want to do 20 up to 25. My integral is with respect to x, it's dx. So let's just dive in here. If we remember what the rule was, it was 0.4 times the square root of the variable, which is x, and then multiply it by cosine of 0.06 times that variable x. I'll now close out those parentheses and hit enter. So what I end up with here is a numerical approximation of this definite integral 2.0431 and so on. So since we're keeping track of our work, this is going to be 71 plus approximately 2.0431, so on, so on. I just need to make sure I have enough decimal places. And if I do this, this will end up with 73.0432, 3 decimal places. May as well throw down my units, degree F. And there we have it. So how are our points divvied up? Well, we got 1 point for writing down an integral, something like that, really applying our net change theorem. And then we got 1 point for our final answer, okay, adding on that initial value of 71 degrees. So how did you get on with this first FRQ on the 2012 exam? If this was the first question you were seeing on your exam, would you be happy, sad, concerned? Either way, this is why we practice them, to maximize your chances of the first problem all the way through the 6th FRQ being ones that make you happy, not sad. So with that in mind, I'll put a link here to the complete playlist of all of the FRQs on this exam. And if you haven't seen it yet, I've also got complete run-throughs of all of the multiple choice questions from this exam too. So I'll put a link to that playlist here as well. But without anything left to say, I would just encourage you to check out that next FRQ if you haven't already on that playlist. And I'll look forward to seeing you shortly.